This is the start of chapter 3.7, and it is all about factoring completely. And so, let me give you an example of factoring completely. So if we had just a quadratic x squared plus 5x plus 6, say, I'm just going to say that that is equal to y. So I know if I graph that, it makes a parabola. And the thing that I know also is when y is 0, and I don't know where these points are, these axes are arbitrary, the x values are those intercepts there and there. So one thing that we've done before in the course before this is when this was set equal to 0, it's x squared plus 5x plus 6, and then we just go to solve it, and we could solve it by using quadratic formula, but we could also factor it. And factor it. This is a pretty easy one to factor. We need things that multiply to 6, but add to 5. That would be 2 and 3. 2 times 3 is 6. 2 plus 3 is 5. So that would be, sorry, that keeps popping up, x plus 2, ugly x, and x plus 3 equals 0. So this part right here that's the factored part. That's it in factored form. So if we just wanted it factored, we'd rewrite it as y equals, or f of x, depending on what notation we're using. That's in factored form. But we keep going from here when it's equal to 0, and we find the zeros, or the x-intercepts. And we know that these two things are multiplied together to give us 0. So this could be a 0, and that happens when x is -2. And I'll conveniently use that. And when this could be a 0, that happens when x is -3. So -2 and -3 are the zeros of this, or the roots. We'll stick with calling them the zeros. And this is it in factored form. So let's take a look at another one. Like if I had something that was something like y equals x squared plus 2x plus 5, say. I could go and try and factor that and try and get things that I got to get rid of this. I could go and factor this, or try to, but I don't have any things that multiplies to 5 to adds to 2, so I'm going to have to use quadratic formula. And remember, quadratic formula is negative b plus or minus square root of b squared minus 4ac all over 2a. And in this case, a is 1, b is 2, c is 5. So plug those in. -2 plus or minus the square root of b squared, b is still 2, minus 4 times a is 1, times c, which is 5, all over 2a. Wow! A is 1. So I'm going to keep going with that. And I get this -2 plus or minus square root. 2 squared is 4, minus 20, all over 2 times 1 is 2. So I'll keep going from here. -2 plus or minus, that's over 2. 4 minus 20 is -15. So notice I get an imaginary number here, a complex number. So my roots are -2 plus or minus square root of 15i over 2. Now here's what I want you to notice with this. This is two different two different answers, the plus one and the minus one. So let me do some erasing here. Make a little bit of space for myself. Thank you for your patience. And I'm going to rewrite this as the two answers that it is. One of them is -2 plus square root of 15i. And that's all over 2. I'll just write them both over 2 like that. I could write it either way. And then I have a minus case too. -2 over 2. I know that's a -1, but over root 15i over 2. Here's the point. If I get one imaginary root, if I know I have one imaginary 0, I have the other one as well. The plus case and the minus case, they will always come in pairs. So that actually gets me to a point here, which is if a plus bi, a and b are just numbers, is a root, is a 0. I should stop calling it a root. It's really a 0. Then a minus bi is also. This is called conjugate zeros. Imaginary zeros will always come in conjugate pairs. Always. So for instance, if you know that 1 plus 2i is a 0, that means that 1 minus 2i also has to be a 0. It has to be. They come in pairs. And one place to see that is in the quadratic formula. When you're solving quadratics, you have this negative b plus or minus square root of b squared minus 4ac all over 2a. Notice everything changes the same except the plus or minus. So if the plus case is a 0, the minus case has to be a 0 as well. Or also, like if 5i is a 0, then that means that negative 5i has to be a 0 as well. It's just like that a is a 0, so it's like a plus this, a minus that. Imaginary zeros, always come in pairs. So what that lets us do is, let's say that I know that I have a quadratic, right? And so that means it has a x squared in it. And I know that 3i is a 0. And then I want to write the equation for it. So this is what I know. If 3i is a 0, then negative 3i must be a 0 as well. So what I could do is I could say, well, that would have to come from x plus 3i, right? That negative 3i makes this a 0, times x minus 3i. That makes this a 0 as well. And then I could just multiply it out. X times x is x squared. X times negative 3i, negative 3xi. 3i times x is positive 3xi. And then 3i times negative 3i. Let's do that one over here. Negative 3i times 3i. 3 times negative 3 is negative 9. I times I is I squared. I squared is negative 1. So this is the same as negative 9 times negative 1. Negative 9 times negative 1 is 9. So that'll be plus 9. And notice that this spills out to a 0. So I'm left with x squared plus 9. And I'll say y equals that. This quadratic would have these zeros. In other words, when y is 0, it would solve to this.